Hello. In this video, we are going to take a look at the general structure of feedback systems, as well as become familiar with some of the terminology pertaining to feedback systems. I have drawn a generic signal flow diagram of a feedback amplifier. We have a source which provides an input signal, and I'm not going to refer specifically to whether the input signal is a voltage or a current. It could be either, so I'm just going to refer to it as X. So X sub S will be the signal from the source, and that signal is fed through an amplifier, which I have labeled by its amplifier gain A, and then it produces an output signal, X out, which is sent into a load. In a feedback amplifier, that sample signal is, or that output signal, is sampled or sensed, which is indicated by this connection here, and it's fed to a feedback network represented with the beta Greek letter. And so that generates a feedback signal, X sub F, which is then subtracted from the source signal and fed back into the input. To generate, X sub I, which can be confusing. It's not the input signal from the input source, that will be X sub S, but rather the input signal to the amplifier, sometimes referred to as the error signal, because it is the difference between the source signal and the feedback signal. So sometimes Xi is referred to as the error signal, and you will see it represented as X sub E sometimes because of that. Let's first learn some terminology. The factor A, capital A, that we have labeled there as the gain of that voltage amplifier, it's referred to as the open loop gain. It is the gain of the amplifier when we don't have the feedback network. So if you just have the amplifier, the box labeled A, you provide an input signal, you get an output signal. That output signal is equal to A times the input signal. So if you had the circuit in an open loop, that will be your gain, and that's why it's referred to as the open loop gain. That's the first term, A, and we know that the gain is basically the ratio of output signal to input signal. Notice that this is A times Xi is whatever gets fed into the amplifier. If we don't have the feedback network, then Xi will be equal to Xs, but technically speaking, it's going to be equal to the open loop gain times the input signal as it is seeing at the input of the amplifier. Now, as we mentioned, the output is sensed or sampled and fed into the feedback network, where it gets multiplied by the feedback factor beta. And so we have that the feedback signal is equal to beta times the output signal. Now, what happens to that feedback signal then is that it gets subtracted from the source signal to generate the error signal Xi. So the feedback signal Xf is subtracted from the source signal Xs to generate the error signal Xi, which is equal then to Xs minus Xf. Okay, and this Xi is the real input to the feedback amplifier. So Xi is the input to The feedback amplifier, sometimes referred to as the closed loop amplifier. All right. So we have the input to the amplifier, Xi, to the feedback amplifier. Let me highlight some of those terms. So we had the open loop gain, the feedback factor, and then we had the feedback signal. I'm going to do those a little different. The source signal and the error signal. Okay. So let's continue. So for the closed loop amplifier or the feedback amplifier, the input signal is Xi, which we just saw is equal to Xs minus Xf, source signal minus feedback signal. And we just stated that the feedback signal is equal to the feedback factor times the output signal, beta times Xo. So we can express this as Xs minus beta times Xout. And the output signal for my feedback amplifier, Xout, is going to be equal to the gain, A, the open loop gain, times the input signal. And so it's going to be equal to A times Xs minus beta Xout. Now from this last equation, I can group all my Xout terms on one side of the equation and all the Xs terms on the other side of the equation. And so I will have Xout times 1 plus A times beta is equal to A times Xs. And the reason why I want to do that is because I want to calculate the closed loop gain of my feedback amplifier. And the closed loop gain is the gain of the amplifier when the feedback network is connected, when the loop is closed, the feedback loop. And so that's going to be, I'm going to represent as A sub F for feedback. And it's going to be equal to Xout over the original signal source. And I can see from this last equation I just wrote that that's going to be equal to A divided by 1 plus A times beta. And this is an important result. And so I'm going to highlight it. So that is again my closed loop gain. And notice that it is related to my open loop gain A. However, we can see that if A is sufficiently large, then I'm going to be able to approximate my closed loop gain by a factor of 1 over beta. So let's take a look at that. So I'll have my in many circuits or in many circumstances, we have that AB is much greater than 1. And therefore my A sub F can be approximated as A divided by A times beta, which is approximately equal to 1 over beta. Which is an important approximation. Why? Well, it's because notice that for large values of AB, I will have that my closed loop gain, A sub F, is virtually independent of the open loop gain and is simply dependent on the feedback network, the feedback factor beta. And so important result, it means for large values of open loop gains, AF is virtually independent of A and only depends on feedback network. Now, why is that important? Well, the reason why we care about that, especially in integrated circuit design, is because the open loop gain, which is the gain of the amplifier, is going to be a parameter that is extremely dependent on variations in process and variations in temperature, whereas the feedback network is typically going to be comprised of passive components that are externally connected, external to my IC. And so I'm going to be able to control them. Let's imagine they are resistors. I'm going to be able to control them and get more accurate results or get smaller tolerances in those resistors that I'm going to be able to get for the gain of my amplifier, the open loop gain. And so basically what I have done is it's called gain desensitization. So I have made the gain of my amplifier much less dependent on process parameters, or much less dependent on the open loop gain. The trade-off there is that I have given up some gain. Obviously, my closed loop gain, A sub f, is going to be divided by a factor of, it's going to be the open loop gain divided by a factor of 1 plus A times beta. And so it's going to be smaller than simply A, than simply the open loop gain. And so I have traded gain for stability. Okay. So basically, reduction in gain but increase in stability, AF, less dependent or independent of process variations, etc. All right, so that is the important result that I have achieved by applying negative feedback. Now the term AB, or A beta, I should say, receives a special name. That's termed the loop gain. Notice that it is the gain that I get if I go around the loop. It's going to be A times beta, the product of the two gains. And so AB receives a special name, as we have said, the loop gain. And then the term 1 plus AB, A beta, also receives a special name. And the reason for that is that it's going to appear over and over again. It's called the amount of feedback, because as we will see, is the amount by which the gain gets decreased, is the amount by which the input or output resistances get increased or decreased, is the amount by which the gain becomes desensitized, etc., as we apply feedback. And so it's just termed the amount of feedback of a circuit. So amount of feedback one plus A beta. And so hopefully this gives us enough vocabulary so that we are speaking the same language as we talk about feedback systems. Let's go ahead and mention a few of the reasons why the loop gain A times beta is an important quantity. So we have importance of loop gain, which is the product of A times beta. And the first reason why it is important is because it is the loop gain that is going to determine or allow us to determine whether we are encountering positive feedback or negative feedback. Specifically, the sign of the loop gain determines the polarity of the feedback. And essentially, if AB is positive, then we have negative feedback. Otherwise, if the loop gain is negative, we have positive feedback. The reason for that is because if the loop gain is positive, it means that the feedback signal will have the same polarity as the source signal, and when it gets subtracted from the source signal, you will end up with a smaller number. Whereas if you have a feedback signal whose polarity is opposite of the source signal, once you subtract it from the source signal, you're actually, a minus, a negative quantity will give you a plus, and so you're adding, so you're increasing your source signal, and that's going to give that regenerative or positive feedback. So the sign of the loop gain allows us to determine the polarity of the feedback. There is a specific method for determining the type of feedback, which consists of opening the feedback loop at some point, applying a test signal, and looking at the polarity of the test signal or the polarity of the signal that you recover as you go through the loop. Second thing is that the magnitude of the loop gain is going to determine how close our closed loop gain is to the ideal value of 1 over beta. AF is to ideal value 1 over beta. Obviously, the magnitude of the loop gain also determines the amount of feedback. Since the amount of feedback was just 1 plus the loop gain. And again, this is going to allow us to measure the improvement in different parameters. So I'm going to say which relates to the improvement in different parameters as a result of negative feedback. And then finally, we have mentioned that A times beta, its polarity determines the polarity of the feedback. But as we go through the loop, A times beta is going to be a function of frequency. And so as the loop gain is a function of frequency, what's going to happen is that phase shifts are going to cause negative feedback to, in some occasions, become positive feedback. It's a function of frequency. Phase shifts may cause negative feedback to become positive feedback, basically a change in polarity of that loop gain. And therefore a lot of the circuit techniques that we are going to study to compensate for this problem are going to be trying to affect a change in the frequency response of the feedback network, and therefore trying to change the loop gain A times beta. All right. Another thing to mention, we have also, we were talking about our error signal. Maybe I will put this as a note. So note that the error signal is also going to be equal to the source signal divided by the amount of feedback. Ideally, when A times beta is very large, the error signal, x of I, will become equal to 0. And so as AB, right, beta tends to infinity, x of I tends to 0. And if you remember, this is what happens in the amplifiers that we build with op-amps. When we have an op-amp connected in negative feedback, we make the assumption that both input terminals are sitting at the same voltage, or that the error signal between those input terminals is equal to 0. And this is because of the feedback. And how close to 0 we get is going to be determined in part by the loop gain, or the amount of feedback. And finally, it can be shown that the gain desensitization for a given circuit is, in the case of the closed loop circuit or the closed loop amplifier, is going to be improved with respect to the open loop amplifier by an amount also related to the loop gain. So specifically, the maximum error in the gain of the feedback amplifier due to process variations or changes in open loop gain is going to be equal to the error in the open loop gain divided by the amount of feedback, 1 plus A times beta. So that's another result that is important because it indicates that we have made our gain independent of variations in the open loop gain, essentially, or at least we've improved that by an amount of 1 plus A times beta. And that's it. We are ready now to get started with the different negative feedback topologies, which we will see in the next video. Thank you.